For years, the conversation about body fat has been framed around willpower, restriction, and effort. We have been told that fat loss is simply a matter of eating less and moving more, as though the body were a passive machine responding only to calories in and calories out. But modern biology reveals a far more hopeful and empowering truth. The human body is not just a storage system for fat, it is a dynamic, intelligent network of metabolic pathways that can be guided, supported, and even reprogrammed by what we eat. Every cell in the body constantly senses nutrients. These signals influence hormones, inflammation, energy production, and gene expression. Some foods quietly push the body towards storing energy, slowing metabolism, and maintaining fat reserves. Others do the opposite. They activate thermogenesis, improve insulin sensitivity, reduce inflammation, and signal the body to access stored fat for fuel. In this way, nutrition becomes more than calories, it becomes information. And that information shapes whether the body is in a fat-storing state or a fat-burning state. This perspective changes the emotional experience of weight and metabolism. Instead of battling the body, we begin to work with it. Fat accumulation is no longer viewed as failure or lack of discipline, but as a biological response to signals the body has received over time. And if signals created the state, new signals can help shift it. Certain foods contain compounds that activate brown fat, enhance mitochondrial function, support gut bacteria that influence metabolism, and regulate hormones that determine how energy is partitioned. The body listens to these cues continuously. The concept of reprogramming metabolism is not about forcing rapid change. It is about creating an internal environment in which burning fat becomes easier, more natural, and more sustainable. When inflammation decreases, insulin stabilizes, and mitochondrial efficiency improves, the body begins to access stored energy more readily. Hunger signals become calmer, energy levels become steadier, cravings often diminish. The shift is subtle, but profound fat loss emerges as a byproduct of metabolic balance rather than a product of constant restraint. One of the most powerful influences on this metabolic programming is the microbiome. Trillions of microbes in the gut participate in extracting energy from food, regulating appetite hormones, producing metabolic signals, and influencing inflammation. The composition of this internal ecosystem changes according to diet. Fiber, rich plants, polyphenol, rich foods, fermented foods, and certain healthy fats nurture microbial communities associated with leanness and metabolic flexibility. Highly processed foods and excess refined sugars encourage microbes linked to energy storage and inflammation. Thus, feeding beneficial microbes becomes another way of guiding the body toward fat burning. Another dimension of metabolic programming lies in the activation of cellular energy systems. Mitochondria, the structures that convert nutrients into usable energy, respond to compounds found in specific foods, compounds that can enhance their efficiency and capacity. When mitochondria function optimally, the body becomes better at oxidizing fat. This is not a temporary effect, it represents a shift in metabolic preference. The body becomes more comfortable using fat as fuel, both at rest and during activity. Importantly, this approach reframes fat loss from deprivation to nourishment. Instead of focusing on what must be removed, attention shifts to what can be added, foods that support metabolic health, hormonal balance, and microbial diversity. This inclusion-based strategy tends to be more sustainable because it aligns with physiology rather than opposing it. The body is not forced into deficit, it is guided into efficiency. When we understand that foods can influence whether genes related to fat storage or fat burning are expressed, nutrition becomes an active dialogue with biology. Each meal becomes an opportunity to send signals that favor metabolic flexibility. Over time, consistent signals accumulate and the body adapts. The metabolic set point, the tendency to store or burn, begins to shift. Thus, the idea that foods can reprogram the body to burn fat is not metaphorical. It is rooted in measurable biological processes: enzyme activation, hormonal modulation, mitochondrial adaptation, and microbial ecology. These processes unfold gradually but reliably when supported by consistent dietary patterns. The outcome is not merely weight change, but improved metabolic resilience, the ability to maintain energy balance with less strain. So the invitation is not to fight fat, but to change the conditions under which it is regulated. By choosing foods that signal burning rather than storing, efficiency rather than inflammation, balance rather than excess, we participate in guiding our metabolism toward its natural capacity for equilibrium. And in that equilibrium, fat loss becomes less of a struggle and more of a reflection of a body functioning as it was designed to function: responsive, adaptive, and capable of transformation. For much of modern culture, the human body has been described as though it were fixed, genetically predetermined, metabolically stubborn, resistant to meaningful change. People are often told that their metabolism is slow, that their tendency to gain weight is inherited, that fat storage is simply their biological destiny. This narrative can feel discouraging because it implies that effort may yield only limited results. Yet contemporary science reveals a profoundly different reality. The body is not fixed, it is metabolically programmable. And one of the most powerful programming languages it understands is nutrition. Every time we eat, we are not merely providing energy, we are delivering biochemical signals. Nutrients interact with receptors, enzymes, hormones, and even gene expression pathways. Certain compounds in food can activate metabolic routes that increase energy expenditure, enhance fat oxidation, or improve insulin sensitivity. Others can push metabolism towards storage, slowing energy use and promoting fat accumulation. In this sense, food acts less like fuel poured into a tank and more like instructions entered into a complex biological system. The concept of metabolic programming rests on the principle that physiology adapts to repeated signals. When the body consistently receives signals associated with abundance and rapid energy absorption, such as refined carbohydrates, excess sugars, and ultra-processed foods, it shifts towards storage efficiency. Insulin rises frequently, fat cells become more receptive to storing energy, and metabolic flexibility diminishes. Over time, the body becomes practiced at conserving rather than burning. But when the signals change, when meals deliver fiber, phytonutrients, healthy fats, and slowly absorbed carbohydrates, different pathways become dominant. Insulin stabilizes, inflammation decreases, and cells become more willing to access stored fat. The body adapts in the opposite direction. This adaptability reflects a deeper biological truth. Metabolism is not a single speed but a network of adjustable processes. Hormonal systems regulating appetite and storage, mitochondrial activity determining energy use, and enzymatic pathways controlling fat oxidation all respond to environmental cues, especially diet. These systems evolved to help humans survive fluctuating food availability. They are therefore inherently plastic, capable of shifting between storage and utilization modes. Nutrition can nudge them toward one state or the other. Understanding the body as programmable transforms the psychology of fat loss. Instead of perceiving weight regulation as a battle against an uncooperative organism, we begin to see it as a process of guiding internal conditions. Fat storage becomes less a personal failure and more a biological response to signals the body has interpreted as needing conservation. When those signals change consistently, physiology changes accordingly. The emphasis moves from restriction to reconditioning. Importantly, metabolic programming does not imply instant transformation. Biological systems adjust gradually through repeated exposure. Just as prolonged intake of storage, promoting foods can shift metabolism toward efficiency in fat retention. Sustained intake of metabolically supportive foods can shift it toward fat utilization. The process resembles training rather than forcing. Cells learn new patterns of fuel use. Hormones recalibrate. Appetite regulation stabilizes. The body's default tendency evolves. This perspective also highlights why short-term diets often fail to produce lasting change. Temporary restriction may reduce calories, but if underlying metabolic signals remain largely unchanged, the body returns to prior programming once restriction ends. Sustainable change emerges not from intermittent deprivation, but from consistent nutritional information that reorients metabolic pathways over time. Programming is cumulative, it reflects patterns, not isolated meals. Viewing the body as metabolically programmable restores a sense of possibility. Genetics influence predispositions, but they do not dictate fixed outcomes. Gene expression itself responds to environmental inputs, including diet. Nutrients can activate or suppress metabolic genes, affecting fat storage, energy expenditure, and inflammation. Thus, nutrition participates directly in how biology is expressed, not merely in how many calories are consumed. When people begin to nourish themselves with foods that signal metabolic balance, foods rich in fiber, polyphenols, micronutrients, and beneficial fats, the body gradually shifts its internal state. Energy regulation becomes more stable. Fat oxidation becomes more accessible. Hunger and satiety cues align more closely with physiological needs. What changes is not only weight, but metabolic behavior. The organism moves from conserving to utilizing, from storing to mobilizing. To recognize that the body is metabolically programmable is to replace inevitability with adaptability. It affirms that physiology responds to repeated nutritional messages, and it invites a gentler, more strategic approach to fat loss, one based not on coercion, but on guiding the body toward its inherent capacity to regulate energy effectively. If the body is metabolically programmable, then the next question naturally arises: what are the signals that guide it toward burning fat rather than storing it? The answer lies in the remarkable reality that specific foods contain bioactive compounds capable of activating the body's fat-burning machinery. These are not stimulants or shortcuts, but nutritional signals that interact with metabolic pathways shaped by evolution. In other words, certain foods don't merely provide calories, they help determine how those calories are used. One of the central mechanisms through which foods promote fat burning is thermogenesis, the process by which the body converts energy into heat. This process is strongly influenced by brown adipose tissue, or brown fat, a specialized form of fat that exists not to store energy but to expend it. Unlike white fat, which accumulates excess calories, brown fat contains dense mitochondria that actively burn fatty acids to generate heat. Research shows that compounds found in foods such as chili peppers, green tea, and certain plant polyphenols can stimulate pathways that increase brown fat activity or encourage white fat cells to adopt brown-like characteristics. When this occurs, the body's baseline energy expenditure rises, subtly favoring fat utilization. Another pathway involves insulin sensitivity, a key determinant of whether the body stores or burns energy. Insulin's role is to signal cells to absorb glucose and, when energy is abundant, to store excess as fat. Diets dominated by rapidly absorbed sugars and refined carbohydrates keep insulin elevated, encouraging storage and reducing access to fat reserves. In contrast, foods rich in fiber, healthy fats, and slowly digested carbohydrates moderate insulin release. This stabilization allows cells to draw more readily from stored fat between meals. Over time, improved insulin sensitivity shifts metabolism toward greater reliance on fat oxidation rather than continuous glucose dependence. Inflammation also plays a decisive role in fat regulation. Chronic low-grade inflammation, often driven by ultra-processed foods, excess refined oils, and metabolic stress, interferes with hormonal signaling related to appetite and energy use. Inflamed tissues tend to become resistant to metabolic cues, including insulin and leptin, creating a state in which fat storage persists despite adequate energy. Anti-inflammatory foods such as berries, leafy greens, omega-3 rich sources, and polyphenol-dense plants help quiet this inflammatory background. As inflammation subsides, hormonal communication improves, and metabolic pathways governing fat breakdown function more effectively. At the cellular level, certain nutrients directly influence mitochondrial function. Mitochondria determine how efficiently cells convert fuel into usable energy, including the oxidation of fatty acids. Compounds in foods like green tea, cruciferous vegetables, and colorful fruits have been shown to support mitochondrial biogenesis and efficiency. When mitochondria are abundant and active, cells become more capable of burning fat as a primary fuel source. This does not create dramatic, immediate weight loss, but it establishes a metabolic environment in which fat utilization becomes physiologically preferred. Importantly, these pathways do not operate in isolation. Foods that activate thermogenesis often also reduce inflammation, improve insulin signaling, and nourish the microbiome. The combined effect is a coordinated shift in metabolic state. The body becomes less oriented toward conserving energy and more toward mobilizing it. Hunger patterns stabilize because energy access improves. Cravings diminish as blood sugar fluctuations decrease. Fat burning emerges not from force but from alignment between diet and biology. Thus, the idea that foods can activate fat-burning pathways reflects measurable biochemical processes: stimulation of brown fat, stabilization of insulin, reduction of inflammation, and enhancement of mitochondrial activity. When these processes are supported consistently, the body gradually adopts a metabolic posture that favors fat use over storage. In this way, nutrition acts as a regulator of metabolic direction, guiding the body toward its innate capacity to access and expend stored energy. To understand why some bodies tend to store fat while others more readily burn it, we must look beyond calories and examine three deeply interconnected forces that govern energy regulation: metabolism, inflammation, and insulin. These systems form a biological triangle that determines whether energy is stored or mobilized. When they are balanced, the body shifts naturally toward fat utilization. When they are disrupted, fat storage becomes more likely, often independent of conscious effort. Metabolism, at its core, is the sum of chemical processes that convert nutrients into energy and maintain cellular function. It is not a fixed rate but a responsive network influenced by hormones, nutrient availability, and cellular health. When metabolic pathways operate efficiently, the body can switch between using carbohydrates and fats as fuel, a property known as metabolic flexibility. This flexibility allows fat reserves to be accessed between meals and during periods of lower glucose availability. But when metabolism becomes inflexible, often due to persistent high insulin and inflammation, the body grows reliant on continuous glucose supply. Fat remains stored not because it cannot be burned, but because metabolic signals discourage its use. Insulin is central to this process. It is often misunderstood solely as a blood sugar hormone, but its broader role is energy allocation. When insulin rises, it signals abundance as cells absorb glucose, the liver synthesizes glycogen, and excess energy is directed into fat storage. Occasional insulin elevation is normal and necessary. The problem arises when insulin remains chronically elevated, as occurs with frequent intake of refined carbohydrates and sugars. In this state, the body receives a constant message to store. Access to fat reserves becomes metabolically restricted because insulin suppresses lipolysis, the breakdown of stored fat. Even when energy intake decreases, elevated insulin can make fat mobilization inefficient, creating the paradox of persistent fat despite reduced calories. Inflammation intersects with this process in subtle but profound ways. Chronic low-grade inflammation alters hormonal signaling and cellular responsiveness. Inflamed tissues become less sensitive to insulin and leptin, the hormone that communicates satiety and energy sufficiency. This condition, often termed insulin resistance, forces the body to produce more insulin to achieve the same effect. Elevated insulin further promotes storage, reinforcing the cycle. Inflammation also disrupts mitochondrial function, reducing cells' ability to oxidize fatty acids. Thus, inflammation does not merely accompany fat gain. It actively shapes the metabolic environment that sustains it. These three forces, metabolism, insulin, and inflammation, therefore create a feedback system. Poor metabolic flexibility encourages reliance on glucose. Frequent glucose spikes maintain high insulin. High insulin promotes storage and inhibits fat access. Inflammation worsens insulin resistance and mitochondrial inefficiency. The cycle reinforces itself, gradually biasing the body toward conservation rather than utilization of energy. Nutrition has the capacity to interrupt this cycle because foods influence all three components simultaneously. Diets rich in fiber, polyphenols, and healthy fats reduce inflammatory signaling and stabilize glucose absorption. Slower glucose entry moderates insulin release, allowing insulin levels to fall between meals. As insulin declines, lipolysis becomes more accessible, enabling fat to be released and used for energy. Meanwhile, anti-inflammatory nutrients support mitochondrial function, improving the cell's capacity to oxidize fatty acids. Over time, metabolic flexibility improves. The body relearns how to switch fuels. Importantly, this shift is less about dramatic restriction and more about restoring physiological signaling. When insulin patterns normalize and inflammation decreases, hunger often becomes more regulated because cells regain access to stored energy. The body no longer perceives scarcity despite available reserves. Fat burning increases not through force, but because metabolic conditions permit it. Thus, fat storage is not merely a consequence of excess intake, it is a reflection of hormonal and inflammatory context. By influencing insulin dynamics and inflammatory tone through nutrition, it becomes possible to reshape metabolism itself. The body moves from a state that favors storage to one that allows utilization, revealing that fat regulation is governed as much by biological messaging as by energy quantity. Beneath the surface of metabolism, beyond hormones and calories, there exists another powerful regulator of whether the body stores or burns fat: the microbiome. Trillions of microorganisms inhabit the digestive tract, forming a dynamic ecosystem that participates directly in energy regulation, inflammation control, and metabolic signaling. These microbes are not passive passengers, they are biochemical partners. And what they are fed determines the messages they send to the body. The microbiome influences fat regulation through several interconnected pathways. First, gut bacteria help determine how efficiently energy is extracted from food. Some microbial communities are highly effective at breaking down otherwise indigestible carbohydrates into short-chain fatty acids, which the body can absorb and use. In certain contexts, this efficiency can support metabolic health, but when microbial balance shifts toward species associated with energy harvest and inflammation, more calories may be extracted and stored. In contrast, microbial profiles associated with leanness tend to promote balanced energy extraction and improved metabolic signaling. Second, microbes regulate hormones involved in appetite and fat storage. The gut produces hormones such as GLP-1 and PYY, which influence satiety, insulin secretion, and energy partitioning. Beneficial bacteria stimulated by fiber, rich plant foods, and diverse phytochemicals enhance production of these hormones, supporting appetite regulation and improved insulin sensitivity. When microbial diversity declines, often due to low fiber, highly processed diets, these hormonal signals weaken, hunger regulation becomes less precise, and metabolic pathways tilt towards storage. Inflammation provides another crucial link. The intestinal barrier normally prevents bacterial components from entering the bloodstream, but when the microbiome becomes imbalanced, this barrier can become more permeable. Bacterial fragments then enter circulation, triggering immune activation and low-grade systemic inflammation. As discussed earlier, inflammation disrupts insulin signaling and mitochondrial function, creating conditions that favor fat accumulation. Thus, microbial imbalance indirectly shapes fat storage by amplifying inflammatory signals. Nutrition has profound influence over this ecosystem because microbes depend on dietary substrates. Fiber, resistant starch, polyphenols, and certain plant compounds act as prebiotics, nourishment for beneficial bacteria. Fermented foods introduce live microbes that can enrich diversity. When these foods are consumed regularly, microbial communities shift towards species associated with metabolic health, reduced inflammation, and improved insulin responsiveness. Conversely, diets dominated by refined sugars, emulsifiers, and ultra-processed ingredients favor microbial patterns linked to inflammation and metabolic dysregulation. This microbial responsiveness means that feeding the microbiome becomes a strategic pathway for influencing fat metabolism. As beneficial bacteria flourish, they produce metabolites such as short-chain fatty acids that improve insulin sensitivity, reduce inflammation, and enhance gut hormone signaling. These changes ripple outward. Glucose control stabilizes, insulin patterns moderate, appetite cues sharpen, and cells gain improved access to stored fat. The body begins to move toward metabolic flexibility, partly because microbial partners are reinforcing that state. Importantly, microbiome shifts occur gradually through consistent dietary patterns. Diversity grows when a wide range of plant foods is consumed. Stability improves when feeding rhythms are regular and minimally processed foods predominate. Over time, the microbial ecosystem becomes more resilient and metabolically supportive. Fat burning does not increase through microbial action alone, but through the cascade of hormonal and inflammatory improvements microbes initiate. Thus, to feed the microbiome is to shape metabolic direction. The foods that nourish beneficial microbes simultaneously reduce inflammatory tone, enhance hormonal signaling, and improve insulin dynamics, all conditions that favor fat utilization. In this sense, dietary patterns that support microbial diversity act as indirect metabolic programming. They alter the internal ecology in which fat regulation occurs. Understanding this connection reframes nutrition yet again. Meals are not only instructions to human cells, they are also nourishment for microbial partners whose signals influence energy balance. When the microbiome is supported, the body's capacity to regulate fat becomes more coordinated and adaptive. And through this partnership, the shift toward fat burning becomes not merely a cellular event, but an ecological one within the human organism. As we bring these ideas together, a new understanding of fat loss begins to emerge, one rooted not in struggle, but in biology. The body you live in is not rigid or predetermined. It is responsive, adaptive, and continuously listening to the signals it receives. And among the most powerful of those signals is food. Not simply as calories, but as information that shapes metabolism, hormones, inflammation, and even the microbial ecosystems that influence energy balance. When we recognize that certain foods can guide the body toward burning rather than storing, the narrative around fat changes. It is no longer a matter of forcing the body into submission through restriction. It becomes a process of creating conditions in which the body naturally shifts its preferences. Stabilized insulin allows stored fat to be accessed. Reduced inflammation restores metabolic communication. Nourished microbes reinforce hormonal balance. Supported mitochondria improve energy use. These processes converge toward one-state metabolic flexibility, the ability to move easily between fuel sources and maintain equilibrium. This shift is rarely dramatic in a single moment, yet it is profound over time. Small, consistent nutritional choices accumulate into biological adaptation. The body relearns how to regulate appetite, energy, and storage in harmony with its design. Hunger becomes steadier. Energy becomes more reliable. Fat burning becomes less an effort and more a reflection of restored function. What changes is not only weight, but the internal environment that governs it. So the message is ultimately one of alignment rather than control. By choosing foods that signal balance, diversity, and nourishment, we participate in guiding our physiology toward its natural capacity for regulation. Fat loss, in this light, is not imposed from outside, it emerges from within, as the body responds to signals that favor health. And in that response lies a quiet but powerful truth. The same biology that once stored energy can be guided to release it when we speak its language consistently, meal by meal, day by day.